Okay, guys, we continue everything. We learn how to uh, separate all categories of protocol, and we know some concept of this. Now we need to understand IP version 6. IP version 6 is important in terms of its a new feature, and we don't have any practice on it, so it needs more time to learn it and understand it deeply. Okay, in IP version 6 there are several different basic types of IP version 6 address shown in the figure. Well done. Important that you are familiar with them, since some of them are also used by routing protocol. Everything alright? Hello Karim, welcome. Welcome to my life. Here we have a IP version 6 addresses, which categorize with a unicast, multicast, and anycast. In multicast we have assigned, we have a solicit and node. In unicast we have a global unicast, local link local, loopbacks, unspecified, unique, local, and embedded IP version 4. For anycast we don't have anything, just we have a unicast. Hello, welcome. Hello guys, welcome. And here we want to explain one by one what is this. We need to understand IP version 6, as I said. IP version 6 types were this figure, and we go for the explanation. RFC 3585 specify 2000/3 to be global unicast address, a space that IANA may allocate to the regional international registration. A global unicast addresses is an IP version 6 address from global address from the global unicast prefix equivalent to the public IP version 4. So when we talk about global unicast, which means a public IP version for addresses. They are the same, so don't be confused. These addresses are unique and globally routable. The allocation and structure of global unicast addresses enables the aggregation of routing prefix, which limit the number of routing table entries in the global routing table. A global unicast address that is used on links or aggregate upward through organization and eventually to the ISPs. Welcome, guys. Okay. And IP version 6 local link. Here we had global unicast and now global unicast, and we want to talk about local link. Okay, local link addresses use the prefix FE8 slash 10 equality 41310110. Any device that is an IP version device must at least have a link local. Okay, it should be considered that any device have to local link addresses at least. It is important, which is automatically configured by default using EUI 6.4 or the privacy extension, although the local link addresses can be statically configured. Rather, typically have a statically configured link local addresses to make the address more easily recognizable when looking at IP version 6 routing table and examining IP version 6 routing protocol information. Notes on a local link can use link local address to communicate. It is important, guys. I highlighted and pay attention. The nodes do not need globally unicasts. Another nodes do not unicast address to communicate. Link local address are not routable. Guys, please pay attention. Therefore, only stay on the link or network. Hello, George. Welcome. Welcome to my life. And multicast address. Okay, we do this and we want to explain here. Multicast address. Multicast addresses are heavily used in a IP version 6. IP version 6, as there are no broadcast address. Okay, guys. Multicast address is not broadcast address. You can recognize them as a part of prefix. Okay, the prefix of multicast is FF00/8. Link local prefix is this, and global unicast is this. So you need to remember, understand, I don't know, but it should be something similar for you. Okay, there are both assigned and solicited node multicast address. There are both assigned and solicit node multicast address. Routing protocol Routing protocols makes extensive use of assigned multicast address. Assigned multicast address. Okay. Assigned multicast address. Here we talk about this. Assigned multicast address. So routing protocol makes extensive use of the assigned multicast address. So we should attention that if routing protocols need to extend, we use assigned multicast. As we discussed here. Assigned address, multicast address are similar well-known multicast address of what? Of multicast address IP version 4 used by routing protocols such as ERGRP, OSPF. Solicit node multicast here, guys. We are here. Multicast node. Please follow my study. Addresses are used by ICMP version 6 neighbor discovery. ND address solutions similar. Okay, solicit nodes multicast address are used IP version neighbor discovery nodes. So we need to remember that similar to ARP for IP version 4. So node, this is ARP IP version 4, IP version 6. So this is the note. I need to write it for myself. And the address resolution is used to map layer 2 MAC address to layer to a layer 3 IP version address or version 6 address. Link local unique local address. So we read this and read this. Where we are unique local address. We are here, guys. Unique local address are IP version 6 unicast addresses that are globally unique and are intended for local communication. It is not expected to be routable on the global internet and is routable inside of a limit area. It is routable inside of limit area, such as a site. It may also be routed between limit set of a site. The prefix is his. The prefix is this. is used to identify unique local IP version unicast address. Okay, let's read more about unicast, unique local address. Okay, it says here is for IP version unicast address, which is already no, it's used for unicast address, and we need to understand more about it. That are globally unique and are intended for local communication. It is obvious it's not expected to be routable on the. So, what is for? An IP version here. Let me. An IP version 6 unicast local address (ULA) is a non-globally routed address within this range, similar to private. Oh, these addresses are designed for use within a private network and are not. Okay, we know. But what is this? What's for? A new address is a special type of IP version. I think private network. Okay, okay. They are used for internal communication. Okay, this is unique. So unique local add in IP version 6 equal to private add IP version 4. Perfect. Now let's jump into next. Just as in IP version 4, a provision has been made for a special loopback IP version 4 addresses for testing. Okay, guys, we know loopback is for testing, but if we already know about loopback, we need to know about this on IP version 4. Datagrams that are sent to this address loopback to the sending device. In IP version 6, however, there is just one address rather than a whole block for this function. The loopback address is 00000001, which is normally expressed as a 1. Okay. In IP version 4, an address of all zeros has a special meaning in that It refers to a host itself and it used when a device does not know its own address. In IP version 6, this concept has been formalized and the old zeros address is named the unspecified address. This one. This address is used as a source IP version 6 address and typically indicate that absence of a global unicast address or that the source address of the packet is significant. For more information about IP version 6 addressing, see IP version function by Rick is for this book. What's up, guys? Now we need to understand ICMP version 6 neighbor discovery. Here we have some data about ICMP version 6, which said solid node multicast address are used by ICMP 6. Now we need to more understanding about ICMP version 6. Internet Control Message Protocol for IP version 6 is similar to ICMP for IP version 4. Like ICMP version 4, ICMP version 6 use information and error message for testing layer 3 connectivity and to inform the source of any issues such as the network is unreachable. Guys, so information and error message used by ICMP. ICMP version 6 is also a much more robust protocol than IP version 4, counterpart as it includes IP version 6 neighbor discovery protocol as described in RFC 4861. ICMP version 6 neighbor discovery is used for automatic address allocation, address resolution, and duplicate address detection in IP version 6. Guys, we now understand ICMP version 6 do not just for pinging on the, or in a reachable or unreachable network. It used in a different task. ICMP version 6 neighbor discovery is used for automatic address allocation, address resolution, duplicate address detection. Do you want to know what is address resolution, automatic address allocation, and duplicate address detection? The duplicate address detection is obvious, yes? But address resolution, which is already know about it, it is ARP protocol, address resolution protocol, and automatic address allocation is DHCP. Do you remember? Somebody remember about that? Okay. ICMP version 6 neighbor discovery includes 5 messages. 1. Rather let me pronounce this word. because it's so annoying. I don't know about it.
Solicitation.
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 Solicitation. Router solicitation RS sent by a device to the all IP version 6 routers multicast to request a routing advertisement message from the router. This is the one of the 5 message which ICMP shows you. First one is router solicitation sent by a device to the all IP version 6 routers multicast to request a router advertisement message from the router. So this is IP version 6 router multicast. Routing advertisements RA sent by IP version 6 router. First one sent by a device, yes. The second one is router advertisement RA sent by IP version 6 router to all IP version 6 devices multicast. Includes link information such as prefix, prefix length, and default gateway address. 3 things, guys. Prefix, prefix length, default gateway. The RA also indicates to the host whether it needs to use a stateless or a stateful DHCP server. Guys, somebody know what is different between a stateless and a stateful? When you assign an IP, we have two different things: a stateful and a stateless. Okay, a stateful and a stateless refer to how IP version 6 address and other configuration information are assigned to a device. A stateful assign requires a DHCP server to track and assign address and other parameter to host, providing central control. A stateless assign most commonly using a stateless address at the configuration SLAAC also devices to generate their own address based on the network prefix from a router, with no central server keeping a list assigned IPs. So this is the difference between a stateful and a stateless. A stateful address, a stateful DHCP servers use assign a IP version, address, and other network parameters like DNS server to a host. Tracking. The server maintains a state, meaning it keeps a record of which address is assigned to which device. Include list time. Control. Provide centralized control over address assignment, make it easier to manage and track a specified address on the network. A stateless address. We have also hybrid. Is okay. Do you want to search IP version 4? Here there is no different, but you need to understand all of them. A stateful is firewall or DHCP track the connections history and details to make a decision, while a stateless methods such as basic address control list or a stateless address auto configuration evaluate each packet and assign independently based on the header. Stateful, a system that maintains a record of the connection's states, include information about active connection, sequence number, and other data. A stateless, a system that treats each packet or request independently without maintaining any memory of previous interaction. Mm, okay. And neighbor solicitation NS sent by a device. Well, this is also sent by a device to the solicited node's multicast address. Guys, look at this picture. Solicited nodes. And what is neighbor solicitation and NS? Hello guys, welcome. Welcome guys. Hello. Okay, let's focus and continue. What is illness? Guys, could you hear me? My voice is clear? Somebody tell me on the chat. Who's here, guys? My voice is clear, guys. Hello, welcome to my live. Welcome. Let's focus. Neighbor solicitation. Send by a device to the solicitation node a multicast address when it knows the IP version 6 address of a device but not its element MAC address. Guys, it is knows the IP address of a device but not evaluate with like Ethernet MAC address. This is similar to address resolution ARP. Similar, not the same. So you need to know. And neighbor advertisement NA sent by a device. This is sent by device also. Oh my god. Usually is a response to the neighbor solicitation neighbor message. So this is the answer or the response of this message. Solicitation message sent as a unicast. It informs that reception of its Ethernet MAC address associated with the IP version 6 address in the MS message. Here and here we need to understand this is in IP version 6 is equal with Ethernet MAC address associated and redirect. This has similar function as in IP version 6 sent by a router inform that source of a packet of a better next hop router on the link that is closer to their destination. It is obvious. And network type, guys. We have a point-to-point broadcast NBMA. Not all layer 2 network topologies support all traffic type because unsupported traffic type influence that operation of routing protocol. It is important to be aware of limitation of specific network topologies. As shown in the figure, there are three general network type described feature in the list that follows. Point-to-point network here. As we can see, let's before read the explanation, let's look at this picture, point to point, which means we have R1, R2, they directly connected to each other. So if two routers see each other directly, they are point to point. Let's read about it. Maybe we wrong, maybe we correct definition. A network that connects a single pair of routers, a packet that is sent from one end is received exactly by one reception on the other of the link. A serial link is an example of point-to-point connection. So guys, here I show it with a serial, not copper. It's not copper, guys. It is a serial cable. You want to serial cable? Serial cable is like this. Let me show you. It's like this. It's like this. With here we have a serial cable. We have a one of the port is male and one of this is female. The industrial names is this. Okay. Broadcast network, a network that can connect many routers along with the capability to address a single message to all of the attached routers. Ethernet is an example of a broadcast network. Ethernet. Okay. As you can see, a message sent to all routers in the same network. Non-broadcast multi-access a network that can support many routers but does not have a broadcast capability. The sender needs to create an individual copy of the same packet for each reception if it wishes to inform all connected neighbors. Also, the sender must know the reception address before the packet can be transmitted. frame relay and this transfer model are example of uh, an NBMA network type. While point-to-point and broadcast networks do not present any difficulties for router protocols, NBMA network introduced several challenges. Let's see what NBMA networks has challenges. Routing protocol need to be adapted through configuration is how they perform neighbor discovery. Okay, routing protocol, one of the challenges is routing protocol need to be adapted through configuration is how they perform neighbor discovery. Distance vector protocol need additional configuration which also change the default behavior of how routing information is exchanged between neighbors. This is second problem. This is due to the loop prevention mechanism split horizon that prevent split horizon that prevent the transmit of information that is received on a specific interface from going out of the same interface. In this paragraph, we have a few words which needs to understand it more. Distance protocols. What is distance protocol, guys? In the last live, we discussed about distance protocol. It was actually it is not it was. It is routing protocol classification. Distance vector includes RIP, ERGRP in IP version 4 and IP version 6. This is distance vector. And now it says, let's see what it says. It says distance vector protocol need additional configuration which also change the default behavior of how routing information is exchanged between neighbors. This is due to the loop prevention mechanism split horizon and prevent the transmit of information that is received on a specific interface from going out of same interface. Let's see what is a split horizon. Okay, guys. A split horizon is a loop prevention feature in the distance vector routing protocol that prevent a router from advertising a route back out the same interface it learned it from. Okay. This technique improves network stability by avoiding routing loops and increasing efficiency. While it can be disabled, it generally recommended to leave it enabled to ensure proper network communication. And let's see how it works. A router received routing update from one of its neighbors via a specific interface. According to the split horizon rule, that router will not send that same route information back out the same interface. This is a key mechanism for prevent routing such as a count to infinity problem. Hello, welcome. Sorry, this is my uh, personal information. I can't share it in the public. Thanks for watching my live. MBMA network can use a variety of topologies. The most common are hub and spoke or partial mesh topologies. What is partial? Let me see. This is the partial network, guys. Full mesh, partial mesh. Perfect. Uh, I have a lot of Indian friends here. The Indians are so friendly and so good. I love them. Good night. If you have a question about cybersecurity and network, I would like to discuss about it. We can discuss and share information. And if you like to support me, please press the link of the pin chat message and support me in this way. Thank you. This is because full mesh topologies do not scale well and can become very expensive with a greater number of interconnected locations. Frame relay technology is the most common example of MBA network. Let's see what is frame relay technology. Guys, this is so important. Frame relay technology. Please pay attention. Oh, nice. I also upload my podcast on Spotify. You can hear it on Spotify. Thank you so much. Thank you. What do you study? Are you network engineer or what? What do you study, bro? Okay, firm relay is high speed, cost effective packet switching technology for connecting LANs over a WAN by breaking data into a similar packet called frame. It operates at physical and data link. Perfect. So you're a student. Nice. I'm pretty sure you can get a certificate of ccna. It has two volume, and you need to read it completely. It takes a 6 month, 1 year, never mind. But please read it completely and understand it deeply. If you understand it deeply, I promise you, you will be the best network engineer in the world if somebody read ccna, because it has a fundamental information. And if you have a good and good foundation, you can improve yourself quickly. So please read ccna completely. And I usually read ccna books every 2 years, 3 years, because it updated, and and it keeps you updated. Please improve your fundamental. And every problem of engineers is fundamental. Thank you. Now, guys, uh, I was reading this subject. It operates as a physical and data links layer of the OSI model, and it uses virtual circuits such as a parameter virtual circuit (PVCs) to transmit data efficiently through shared public, often eliminating the need for expensive. Good luck, bro. MBMA network is about this, and here we are here. Frame relay technology is the most common example of an MBA network. There are several options for how you can adopt routing protocol to support operations in a frame relay NBMA hub and spoke network. If you use a single frame relay multi-point interface to interconnect multiply sites, reachability issues may be a problem because of the MBA nature of frame relay. Their frame relay MBA topology can cause the following issues. Okay, what is the issues of NBMA topology? A split horizon. for distance for distance vector routing protocol. Sorry, guys. For distance vector routing protocols, do you remember routing protocol, guys? Do you know distance vector? What is distance vector? Somebody knows? Write it on the chat. For distance vector routing protocols, the split horizon rule reduces routing loops. As illustrated in the figure, it prevents a routing update that is received on an interface from being forwarded out of the same interface. So In a scenario using a hub and spoke firm relay technology, a spoke router sends an update to the hub router that is connecting multi-parameter virtual circuits (PVCs) over a single interface. The hub router receives the update on its physical interface but cannot forward it through the same interface to other spoke routers. A split horizon is not a problem if there is a single PVCs on a physical interface because this type of connection would be point to point. Guys, do you know PVCs? Parameter virtual circuits. Let's focus on PVCs. First, let's zoom in. This is a conceptual of virtual circuit in a computer network. And let's see what is this. A parameter virtual circuit is a pre-configured, always on a logical connection on a packet switch network that remains intact for repeat use without needing to be sent up and torn down for each station. Unlike a switch virtual circuit, which are created and destroyed as needed, PVCs are used for continuous or frequent communicate between two specific points, providing a faster, more consistent connection. Technology like firm relay and ATM are often used implement PVCs. How it works: pre-configuration. PVCs are set up beforehand and maintained for a long-term period by network operator. No setup time. Once established, they are immediately ready to use, eliminating the overhead of setting up and clearing connection for each data transfer. Always on net connection and flexible paths. Now, do you know what is pyramid virtual? Okay. And this is our figure. Neighbor discovery. Okay, these are frame relay NBM topology can cause the following issues. Neighbor discovered OSPF over NBM network work is an non-broadcast network mode by default, and neighbors are not automatically discovered. Okay, guys. Somebody asked me on TikTok, what is MBA network? I should say MBA network NBMA network. Non-broadcast multicast area, bro. This is network is type of computer network that connects multi-devices but lacks of native broadcast and or multicast capability, meaning it cannot send a single packet to all devices at once. Instead, data is sent directly from one host to another via virtual circuit or switch fabric, right? Examples include frame relay and ATM network, and routing protocol like OSPF need manual configuration to identify neighbor NBA. As we discussed it here, OSPF over NBA network works in a non-broadcast networks mode by default, and neighbor are not automatically discovered. It is very important. You need to understand it carefully. You can you can statically configure neighbors, but an additional configuration is required to manually configure. Oh my god, what happened? I lost my screen. And guys, do you have my screen? Hello guys, welcome to my live. Welcome, welcome. Hmm, let's bring it here because I think it's annoying. Now I think it's better. Come on, come here, and I think everything is alright. Perfect. Okay, guys. Where we are, you can statically, you can uh, you can statically configure neighbors, but an additional configuration is required to manually configure the hub as a designated router. OSPF treat an NBA network like Ethernet by default, and on Ethernet, a DR is needed to exchange routing information between all routers on a segment. Therefore, only the hub routers can act as a DR because it is the only router that has PVCs with all other routers. And a broadcast replication is the one of the issues of what is NBA topology. Broadcast replication with the router with the support multi-point connections over a single interface that terminate at multi PVCs. The router must replicate broadcast packet, such as routing update broadcast on each PVC to the remote routers. This replicate broadcast packet consume bandwidth and cause significant latency variation in traffic. One of the most issues of MBA topology is it says actually with router that support multi-point connection over a single interface that terminate multiply PVCs. So we don't have multi broadcast, guys, and this is our problem. And the router must replicate broadcast packets, such as routing update broadcast. It needs to routing update broadcast on each PVC. For this reason, this replicate packet consume bandwidth and significant latency. So the ping or ICMP packet, for example, it face with a lot of latency. When a router is connected to the multi-physical location over a WAN MBA link, you can use the logical subinterface to terminate multicast multiply virtual circuit on one physical interface. Subinterface also overcomes some limitation of MBA network. You can choose between two different type of subinterface. So okay guys, we have a point-to-point subinterface. Each subinterface which provide connectivity between two routers use its own subnet for address. From a perspective of routing protocol, connectivity looks just like a several physical point-to-point links, which means there are no issues with the neighbor discovery and split horizon rules. If you remember, we have a two important problem in MBMA networks. One of them was a split horizon, and one of them was a neighbor discovery. Okay, with the point-to-point subinterface, we solved these problems. So if you look at this figure, we now see the subinterface look every routers independently. So we have a 1.1, 1.5, 1.9 and one physical interface. In here we have a subinterface serial 1.1, 1.2, sorry 0.2, 0.3, which means in a one serial interface we have a three subinterface in a router, and they are completely independent. Another connections is point to multi-point subinterface. Here, do we have any picture of it? No, but we can search it, no problem. One subnet is shared between all virtual circuits because private address space is normally used for addressing. Saving address space is not a significant benefit because both ERGRP and OSPF need additional configuration to support this. Underlying technology point-to-point subinterface are preferred and recommended choice. So guys, this book recommended point-to-point subinterface because private address space is normally used addressing. Saving address space is not significant benefit. Now we are in routing over the internet. Perfect. You can select among several different options and technologies when choosing how to interconnect remote location with a central location such as headquarters site. One of the operations is to rent internet connectivity, which is usually a less expensive alternative. There are several reasons why IGP routing protocols are not used to establish connection over internet. Why, guys? What do you think? Oh my god, what happened? Guys, let's fix this problem because I think we have a lot of lag. I'll come back after 5 minutes.
It means you need to quickly master something, well, something foundational, mission critical, and let's be honest, maybe a little intimidating.
Yeah, definitely foundational.
Today, we are undertaking a deep dive into the protocols that ensure every modern network, from the small office right up to the massive data center, doesn't immediately self-destruct.
That's a good way to put it, self-destruct.
We are diving into the spanning tree protocol STP, and its absolutely crucial evolution, RSTP.
Right, STP and RSTP.
Our sources today, they're packed with mechanical detail, historical context, and really essential configuration nuggets.
And lots to unpack there.
The mission is sharp, it's clear. We are going to extract the core logic, trace the evolution, and really master the configuration features of these protocols.
Yep.
Why? Because redundancy, well, it isn't a luxury in modern networking, it's the expectation, right?
Absolutely. It's table stakes now.
But adding that second path, that failover link, it introduces this almost hidden existential threat that simply must be tamed.
It's exact.
We're exploring exactly how STP and RSTP save networks from that danger.
That analogy, saving the network from itself, it's perfect. Because the conflict is it's absolute. You must have redundant paths for high availability. You just have to.
No question.
But the standard operation of layer 2 switching, just how Ethernet works, dictates that those redundant paths, they create a disaster.
Right.
So STP-RSTP performs this necessary, highly critical balancing act. It preserves connectivity, making sure all devices can still reach each other while, simultaneously enforcing a stable, loop-free topology by selectively blocking those redundant links.
Okay.
We are going from this potential disaster zone to a structure of precision, and we really need to understand the fundamental logic that makes that possible.
Okay, let's unpack this immediately, because the elegance of the solution, you only truly appreciate it when you understand just how severe the problem is.
Definitely.
So what happens if you are, say, courageous network engineer, maybe a bit too courageous, and you add a redundant link between two switches, maybe late on a Friday?
Oh, boy.
And you forget, or maybe you don't know you need to, enable spanning tree. What is that nightmare scenario?
The short answer, and our sources really emphasize this, is sustained chaos. Just complete chaos that brings the entire switch domain to a grinding halt.
Not just slow, but halt.
Oh, yeah. When you introduce a physical loop and have absolutely no loop prevention mechanism, Ethernet frames will just cycle. They loop around the network indefinitely.
Indefinite. Like how long?
I mean, the loop never ends. Not for an hour, not for a day, potentially forever, or, until a switch literally physically fails or someone figures it out and yanks the cable.
Wow. Okay. And crucially, this isn't just about wasting a little bit of bandwidth, is it?
Not at all. That's almost the least of your worries. This single failure mode, this loop, it triggers 3 interconnected catastrophic problems all at the same time.
3 things. Okay, let's start with the loudest one, the one everyone probably notices first.
Right.
The broadcast storm.
Precisely. That's the most obvious symptom. A broadcast storm gets kicked off by any frame that, by its very design, has to be flooded out of all interfaces in that VLAN, except, of course, the one it arrived on.
So things like ARP requests?
Yep. ARP requests, which are broadcasts, IP multicast traffic, and critically, even regular unicast frames, if the destination MES address isn't in the switch's table yet, those are called unknown unicasts.
Right, the switch doesn't know where it goes, so it floods it.
Exactly.
Yeah.
So the switch gets a broadcast frame on port A. Its basic logic says, flooded out ports B and C.
Okay.
That frame immediately hits the next switch in the loop, which does the same thing, floods it again.
And because of the loop.
Because of the loop, the original switch receives that same frame back, maybe on port B or port C this time.
And its own rules say.
Its basic layer 2 logic dictates it must flood it again. There's no intelligence saying, I've seen this before.
So they just multiply.
Exponentially. Within milliseconds, the frames are just replicating like crazy, consuming all the available bandwidth. The links get completely saturated.
Which means no legitimate traffic gets through.
Correct. It crowds out all the good user frames. But more subtly, and maybe even more agonizingly for the end user, think about every connected PC, every server, every IoT device.
They see all this traffic.
They have to process this excessive, unrelenting stream of looping broadcast frames. Their CPUs just get hammered trying to figure out, is this frame for me? No. Is this frame for me? No. Over and over.
Leading to
complete client device performance degradation. Everything just grinds to a halt because the endpoints are too busy dealing with the storm.
Okay, so that's disaster number 1. A network where nothing can get through and all the devices are choking. But you said that's only part of the story. There's a second, maybe more dangerous problem.
Yes. MC table instability. This one is the subtler killer.
How does that work? Normally, switches learn MSE addresses, right?
They do. A switch learns a host's MSE address and associates it with a specific port. Host A is out port 1, nice and stable.
But with loops,
With looping frames, the same frame from the same host keeps arriving on different ports because of that cycle.
oh, I see.
And this forces the switch's MASI address tables to continually update or flip-flop.
Let's use that Bob example from the sources. It was pretty clear.
Yeah, okay. So Bob is connected to switch 3's 501 port. SW3 learns, okay, Bob's MC is on now below 101. Solid entry.
But then Bob sends a broadcast like an ARP.
Right, and it loops. It goes from SW3, maybe over to SW2, then across to SW1, and eventually, because of that redundant link we added.
It comes back into SW3, but on a different port.
Exactly. Let's say it loops back into SW3's redundant port, G01.
What does SW3 do then?
Well, the switch learning process is absolute. It sees Bob's frame arrive on G01 and immediately thinks, wait, I just saw Bob's frame on G01. That must be where Bob is now.
So it updates the table.
It overwrites the entry. It points Bob's MSC address to G01 now.
And the consequence...
Now, if another host, say Larry, tries to send traffic to Bob, SW3 looks up Bob's MC, sees G01, and incorrectly forwards Larry's frame out G01, sending it off into the looping segment towards SW1.
Instead of delivering it locally to Bob on Fazio 3.
Precisely. The traffic never reaches Bob. And then, maybe a few seconds or minutes later, another broadcast from Bob might arrive on the correct port, Faz033.
And it flips back.
And it flips back again. The table is completely unstable because the entries are constantly toggling between the ports on that redundant path. Reliable delivery becomes impossible.
Okay, that sounds really bad. Broadcast storms, unstable MFE tables. What's the third leg of this disaster stool?
That leads directly to the third issue, multiple frame transmitters.
So getting the same data more than once.
Exactly. Even if the network hasn't, entirely melted down yet from the storm or the MSC flapping, let's say Bob sends a unicast frame to Larry, but the switches haven't learned Larry's address yet.
So they flood it, like an unknown unicast.
Right. They flood it. But because of the loop, Larry ends up receiving multiple, identical, unnecessary copies of that single frame Bob sent.
And that causes problems.
Well, it's not just inefficient, it can seriously confuse higher layer protocols like TCP or cause applications running on Larry's machine to fail because they just aren't designed to handle duplicate data streams arriving like that.
Okay, the need is undeniable. Broadcast storms, MSE instability, multiple frames. It's a complete meltdown.
Total meltdown.
So STP has to break that loop. It does this by forcing some of those interfaces into a blocking state.
That's the core idea. Simple in concept, really. Force some interfaces into a blocking state to break the physical loop into a logical tree structure.
We sacrifice the use of an available link. That's the minor negative side effect you mentioned.
Exactly. You don't get to use that extra bandwidth, but you gain total network stability.
And that stability is absolutely the cost of entry for any serious network design.
It is the foundation. Without it, nothing else works reliably.
Okay, so now we pivot from the chaos to the precision. How does the spanning tree algorithm, the STA, actually execute this? How does it build this stable, loop-free topology?
Right. The STA is essentially the sophisticated negotiation process that happens between the switches.
A negotiation.
Yeah, they talk to each other using special messages, BPDUs, to figure out the best loop-free path. It determines which interfaces get the green light, the forwarding state, and which ones have to sit idle in the blocking state.
And the goal is to impose a tree structure. Like mathematically.
Exactly. A hierarchy with a single root, ensuring there's only ever one active path between any 2 points in the layer 2 domain at any given time.
And the protocol relies on, 3 core criteria. For a port to be allowed to forward traffic.
Yes, 3 fundamental rules or steps in the process. Step 1, electing the root switch.
The king of the castle.
Pretty much. This switch becomes the unwavering reference point, the center of this logical tree. And by definition, all working ports on the root switch itself must be placed into a forwarding state. They're the starting point for all paths.
Okay, makes sense. One root, all its ports are active. Step 2.
Step 2, every other switch, every non-root switch, must choose its root port, RP.
Root port, what's that?
The RP is the single port on that non-root switch that provides the absolute least cost path back towards the root switch that was just elected.
Least cost. We'll have to define cost later, but okay.
Yep.
One best path back to the root.
Just one root port per non-root switch. That's crucial.
Got it. And step 3.
Step 3. On every individual LAN segment, so basically every link connecting two switches or a switch and a hub, if you still have those.
Hopefully not.
Hopefully not. On each link the switches connected to it must elect a single designated port, DP.
Designated port. So one port on that link gets picked?
Right. The designated port belongs to the designated switch for that segment. And usually the designated switch is the one that has the lowest path cost to the route.
So it's considered the switch responsible for forwarding traffic onto that segment towards the route or away from it?
Exactly. It's the most efficient path from that specific link towards the route.
Okay, route switch election, route port selection on non-routes, designated port selection on each link. That's the framework.
That's the logical framework. And this entire structure, this whole negotiation, is built upon something called the bridge ID, or BD.
The BD. Okay, let's delve into those election mechanics now, because it sounds like understanding the BID is how you understand control over your topology.
Absolutely. The B by D is everything when it comes to determining the route and influencing paths. It's an 8-byte value, and it has to be unique for every single switch in the network.
8 bytes. How is it structured?
It's a composite value. The first 2 bytes are the priority field. This is the important one for configuration.
Okay, priority.
The next 6 bytes form the system ID. And this is typically derived directly from the switch's universal burned-in MAC address. Usually one of the ASCII addresses assigned to the switch.
So priority plus AMSI address equals BID.
Basically, yes. Although technically the system ID might include a VLAN ID component in some variants, but the core is priority plus unique MC identifier.
And the golden rule for the election, you said it earlier.
Simple. The switch with the numerically lowest bridge ID wins the route election. Lower is better.
Lowest overall 8-byte value.
Yes, but it checks the priority field first. That's the most significant part.
Okay, and the priority field, that's where engineers can step in.
Exactly. By default, Cisco switches often use a priority value like 32,768 plus the VLAN ID, so maybe 32,769 for VLAN 1. It's a high number.
But you can change it.
Yes, you can manually configure a much lower priority value, like 4096 or 8192 or even 0, though that's generally not recommended.
So if one switch has a priority of 4096 and all the others are at the default, say 32,769.
The switch with 4096 wins immediately, hands down. The MAC address part of the BID becomes irrelevant at that point because the priority is so much lower.
So that's how you guarantee your big, powerful core switch becomes the root. You just give it the lowest priority.
Precisely. That's how engineers influence the outcome and make the topology predictable. By lowering the priority, you ensure your chosen, most capable switch becomes the root.
But what if you don't configure it? What if all switches are just left at their default priority? Which I imagine happens a lot in, unmanaged or quickly set up networks.
It happens all the time. In that case, if the priorities tie, then the MAC address portion of the BID serves as the ultimate tiebreaker.
So the switch with the lowest MAC address wins.
The switch with the numerically lowest MAC address wins the entire election. Since MAC addresses are unique globally, this guarantees a winner.
But it's basically a lottery at that point, right? Some random switch, maybe an older, slower one, could end up being the root just because it has a lower AMS.
Exactly. It's unpredictable unless you manually intervene with the priority setting. You might end up with a suboptimal route, leading to inefficient paths.
Okay, so the election process itself, how does that actually happen? Do they vote?
Not quite voting. It's more like a dynamic campaign. Initially, every switch thinks it is the root.
Bit arrogant.
Well, it doesn't know any better yet. So each switch starts sending out special messages called Hello BPDUs. BPDU stands for Bridge Protocol Data Unit.
Hello messages. Okay.
In these hellos, they announce their own BID and claim, I am the root.
Okay.
Now, if a switch receives a hello BPDU from a neighbor, and that hello contains a BID that is better, meaning numerically lower than its own BDD.
It realizes it's not the best candidate.
Exactly. It recognizes that incoming message as a superior hello. At that point, it stops claiming to be the root itself.
And does what?
It stops sending its own hellos claiming root status and instead starts forwarding the superior hello it received. It essentially drops out of the race and starts campaigning for the better candidate it just heard about.
I see. So the better beads propagate through the network.
Right. This process continues, with switches constantly comparing the beads they hear, until eventually everyone agrees on which switch has the absolute lowest BD. Only that one true root switch continues generating hellos claiming to be the root. Everyone else just forwards those hellos.
Consensus is reached.
Consensus is reached.
And those BPDUs, those hello messages, they must carry more than just the BID, right? They're the lifeblood of this whole thing.
Oh, yeah. That hello BPDU is extremely dense with information. It's carrying everything needed to calculate the topology and maintain it.
What's in there?
4 critical pieces of information. First, obviously, the root bridge ID, the BD of the switch the sender believes is the current root.
Okay.
Second, the sender's bridge ID, the BD of the switch that actually sent this specific hello message.
So who the root is and who's telling me.
Correct. Third, the sender's root cost. This is the sending switch's calculated cost to reach the root switch it just named.
The cost we mentioned earlier, how far away they think the root is.
Exactly. And finally, the STP timer values. Things like how often hellos are sent, how long to wait before declaring a neighbor dead, etc. These timers are actually dictated by the root switch itself and propagated outwards in the hellos.
Okay, so